The amount of gravity needed to keep humans healthy over the long term depends on the level of gravitational force that simulates the conditions of Earth gravity, as well as the body's adaptation to long-term exposure to reduced gravity environments, like those in space. Humans are adapted to Earth's gravity, which is about 9.8 meters per second squared, ms squared. This level of gravity is crucial for our physiological functions and health. The body has evolved in this environment, and the following systems are influenced by gravity. Bone density. Gravity provides mechanical load to bones, which stimulates the deposition of minerals like calcium. Without this load, bones can become weaker, a condition called osteoporosis. The weight-bearing forces prevent excessive bone resorption. Muscle mass. Muscles, particularly those of the lower body, rely on gravity to maintain strength and mass. In the absence of gravitational forces, like in space, muscles weaken and atrophy over time because they are not required to work as hard. Cardiovascular system. Gravity also plays a role in blood circulation. On Earth, gravity helps to pull blood down toward the legs, and the heart works against it to pump blood upward. In lower gravity, the cardiovascular system works less intensively, and astronauts can experience a shift in fluid distribution in the body, causing facial puffiness and other changes. Fluid distribution. Gravity helps to keep bodily fluids, like blood, lymph, and interstitial fluids, evenly distributed. In microgravity, fluid tends to shift upwards to the upper body and head, which may cause some negative effects such as increased intracranial pressure. Long-term health risks of reduced gravity. Human health deteriorates over time in low-gravity environments, such as those experienced by astronauts in space. Microgravity. Near-zero gravity, which is the condition astronauts experience aboard the International Space Station, ISS, has been shown to cause a range of health issues. Muscle atrophy. In microgravity, muscles are not needed to support the body's weight, so they begin to weaken and shrink, especially the legs and lower back. Bone density loss. The lack of weight-bearing activity in microgravity causes significant bone density loss, which can increase the risk of fractures. Astronauts lose about 1 to 2% of bone mass per month while in space, with bones like the spine and pelvis being the most affected. Cardiovascular changes. The heart doesn't have to work as hard in microgravity, and it can shrink in size. Additionally, astronauts may experience orthostatic hypertension, dizziness or fainting upon standing, when returning to gravity after spending long periods in space. Vision problems. Changes in pressure inside the skull and shifts in bodily fluids can affect vision. Many astronauts have experienced issues like farsightedness or an increased pressure on the eyes, which can alter eyesight. Gravity for health. What is optimal? Humans evolved with Earth's gravity, so ideally, the 9.8 meters per square second level is optimal for long-term health. However, for situations like space travel or living on other planets, gravity can vary, and strategies need to be devised to maintain health. Here are some general considerations. Partial gravity. On other planets or moons, the gravity would be lower than Earth's but still significantly more than zero. For example, Mars, 0.38 Earth gravity. Mars has about 38% of Earth's gravity, and humans exposed to this level of gravity for prolonged periods may face health challenges, such as muscle and bone weakening, but it would likely be less severe than in microgravity. The Moon, 0.16 Earth gravity. The Moon has only 16% of Earth's gravity, so the negative effects on bones and muscles would still be significant. However, a person could potentially adapt better than in zero gravity, though exercise and gravity-based stimulation would be essential. Potential solutions for long-term space exploration. To mitigate the health risks of reduced gravity during long-term space travel or colonization of other planets, several methods have been proposed. Artificial gravity. One of the best solutions is to create artificial gravity by rotating spacecraft or habitats. By spinning the habitat, centrifugal force would simulate gravity, allowing the body to experience the effects of gravity, at least partially. This approach is understudied but presents engineering challenges. Exercise and resistance training. Astronauts aboard the ISS perform daily exercise regimens to counteract muscle and bone loss. In space, resistance training devices, like treadmills with harnesses and exercise bikes, help maintain muscle mass and bone strength. Pharmaceuticals and nutrition. Scientists are exploring ways to reduce bone loss and muscle atrophy using drugs, supplements, like calcium and vitamin D, and advanced nutrition tailored for astronauts. How much gravity is needed for health? While full Earth gravity, 1 g, or 9.8 meters per square second, is the optimal and natural condition for human health, any level of gravity above zero gravity would likely help mitigate some of the health issues associated with prolonged weightlessness. Here's a rough breakdown. Full Earth gravity, 1 g, best for long-term health, preventing bone loss, muscle atrophy, and cardiovascular problems. Partial gravity, gravity levels between 0.2 g and 0.5 g, as found on the Moon and Mars, would likely require additional interventions, such as exercise, to maintain health. Zero gravity, microgravity, most detrimental to long-term health, leading to muscle atrophy, bone density loss, and cardiovascular issues, unless mitigated with artificial gravity, exercise, or other countermeasures. In conclusion, while Earth gravity, 1 g, is the ideal for human health, lower gravity, like that on Mars or the Moon, could be sustainable for humans with the right interventions. Without gravity, such as in space, extensive countermeasures are necessary to keep humans healthy over the long term.